Okay, so we've just been looking at 1D shapes. So these points here, these bars, we have these points on here. So we've just thought of that as something which maybe has a dimension in the X direction, but not in the Y dimension. So what happens if we have an actual bar, maybe like we did a bit earlier? So we know that the center of mass is going to be a bang along the center if the thing is all the same weight across. But likewise, if we were to rotate this round, we will also find that the center of mass would sit along the center here. So we can use our power of symmetry to help us find this Y bar and this X bar, and that shows us where the center of mass of a 2D object is. Okay, that's quite simple. So likewise, if we did the same with a square, like this, we could find the center of mass by just finding the symmetry line, and that would be here. This would be our centroid. Likewise, if we were to do the same lines of symmetry, we'd find that it crosses here, and we could keep on following this round. And likewise, you might think of the Earth, something like this here. We have our molten magma core here, and gravity is pulling us this towards the center, and this is our central point. You'll actually find that due to some geographical points, so the isostatic equilibrium, and also how the Earth shapes itself, we have different effects of gravity at different points of the Earth. And if you read Hawking's book, you'll find out that affects the aging of someone if they live somewhere high up and somewhere low down. Okay, so that's quite simple, but what happens if we have a shape that looks like this? So we can't actually find simply where its lines of symmetry are. So what we can do is, well, we can split it up into lots of little sections, or we call these lamina. And again, this is looking a little bit like our integration. We now have a set of bars, and from this we can find our central location on this axis, and this would give us our center of mass. So likewise, we can find that our median value, if we were to split this into the other direction, would also fit somewhere along here. So this would help us to identify our center of mass. So this is how computers would do it, and often in a computer, these points would be so small that they would have no effect on the actual calculation. So as I've just mentioned, that this value effectively is the median. And actually, when we have a triangle, we have some great geometrical properties of a triangle. So what we know from a triangle is that the centroid, we're not going to get these confused with center of mass and centroid, but I'm not going to really mention the difference. We'll just see them as the same maybe for this module. Is the centroid, if we have this triangle of which was 9 and which was 6, is always a third of the distance of the triangle. So we can try from the vertex. So we can try this by getting an actual triangle itself and dropping it. And from a geometrical property, if the triangle has a right angle, we know that a third the distance from here, we're going to have the centroid. So that would, in this case, would be 2, in this case would be 3, and this would be the centroid of our triangle, or this would be our center of mass of our triangle. Okay, so that's all right, but what happens if we have some more complicated shapes? We've got triangles. Realistically, in the exam, you're not going to have something as simple as that. I'm not going to be as nice. So what happens if we have a shape that a little bit like in the textbook that looks a little bit like this? It's a compound shape. Okay, so excuse the drawing. So we'll just put the same letters onto it. So F, E, 4A, 4A. We have 2A, we have 2A, and we know that this is D, C, and this is A and B. So we know straight away that our center of masses for each of these individual squares will be here and here. So likewise, we can say that somewhere between these 2 points, the center of mass is going to lie. But as I've just said, we actually want to work out the center of mass in both the Y direction and now in the X direction. Okay, so we have an equation for that, but how can we actually deal with it? We've also been told on this shape that we don't actually know the mass of the things, but we've been told its density. So we know that for a 2D shape that the mass would equal the density times by the area. So density times volume would equal our mass normally, but actually we don't have that. So weight, sorry, would be mass times density. So what we can actually do is we can just put our rho in here. So we could say, if we bring back our equation from earlier, so perhaps we look at our equation where we have our total mn xn equals x bar total m, or we could do the same thing. So we could say that, well, our total masses would have to be 16, and we're actually going about this point 0. This is our thing. So if we put our point 0, And so our first mass will be 16. We know that our center of mass is halfway from here, so that will be multiplied by 2a. Then we want to find the second one, which would be our total mass. So 16a. Oh, sorry, I've skipped a step here. So we can see that our total mass would actually be 4a times 4a, which would be 4a squared, multiplied by our density. And we also want to multiply that by our distance from here to here, which is 2a. I was getting excited then. And we want to add our second one on, which is 2a and 2a. So that would be 2a squared rho. Okay. And that's all squared. And then we can say, right, how are we going to get the next bit? We're going to find our distance. Well, actually, we have 4a here plus half of the 2a, which should be multiplied by 5a. And now we're going to now say that that is equal to our total mass, which is 4a squared plus 2a squared multiplied by x bar. And if we stick that into our calculator, we would find that our x bar would equal 2.6a. So we're having it in terms of a. So likewise, we can do the exact same for the y-axis. And we could say, right, so if we were to rotate this, our total mn yn equals our y bar total n. So we could do the exact same calculation. So we can say that that would be 4 times 4, well, we've got that our 16a squared, so that's 4 squared a squared, multiplied by, well, from the distance from here is, again, it's 2a, so multiplied by 2a, and we're going to plus, but we're going in this direction, so that again is 2a squared, so that's 4a squared rho, I've got the rho again on here, and we can say that we have our distance from here, which is just 1 in this case, multiplied by 1a, is equal to our total masses again, which is our 4a squared plus 20a squared plus 2a squared, which is 20a squared, multiplied by our y bar. And what we can actually find now, using this equation, we've actually managed to find that y equals 1.8a. So we can find that our center of mass would be 1.8 up here, and it would be 2.6a along here. So it'd be somewhere around here. So this would be our center of mass. Okay, so what we can do is we can actually simplify this into a table. I've really overcomplicated this. So if we can think of this as our two squares here, where we have our first square, which looks a little bit like this, and our second square that looks a little bit like this, and we just put our terms back on here again. We can call that was O, F, E, A, and that is B, C, D. Well, perhaps we can actually draw a table to help us calculate this. And if we want to just use our first square, which would be O, A, E, F, and our second one, which would be A, B, C, D, and our total, the actual of the total shape we have, which is O, A, E, F, A, B, C, D, perhaps we'll call that. Well, we could just work out our masses here. So we put our masses in one column, and then we could have our X locations in another column and our Y locations in that column. And we can say our mass of X and our mass of Y. So we could say that would be our mass of this first one would be 16a squared. The mass of our second one, which is 4a squared. We add all of this together. We know that would be 20a squared. What else have we got here? X, our first distance, X from the centroid is that. Likewise in Y, if we have it from here to here, which would be 2a, we would have our distance here, which is 5a from 0, and this is a, and then we can say that our distance, what we're trying to find is x bar and y bar. Our mass are m times x, so we just multiply these two together, and we would get our, actually have two rows on here, our 16a squared rho multiplied by 2a, Likewise, we have our 4a row, our squared row, multiplied by 5a, and we have, if we sum these up, we would have 20 a squared row x bar. And if we were to do the same here, we would say that this would be 16a squared row times by 2a, 4a squared row times by a, and 20a squared row y bar. And then basically we stick this back into our original calculations, and this will give us all the numbers in a quite an easy form. So we would say that our 16a row squared times by 2a squared, 2a is our first value, plus we're working down the table, 4a squared row multiplied by 5a equals our 20a squared multiplied by x bar, and so on, and that would give our same answer as 2.6a. It's just a simple way. However, you might find, as you've just seen with me, it can get quite confusing. If they're simple shapes, you might choose to actually go for just working it out simply. So likewise, here we have another shape in example B. So here we can see our second example, where we have a square and we have a triangle. And we're going to say that this is 2a in distance. We know that this is 3a. And you're going to call this A, B, D, C, and we're going to have a line here, something like this. Okay, so maybe we should have had another letter on here, but anyway, maybe call this E. And we want to find our center of masses, so perhaps we can just make the table, or we can think of this, of what we want. Where we finding this around? We are finding this around, find the center of mass of uniform shape shown in the diagram. And again, we want to find it about point A. So we would say that our mass of our first one, let's draw our table, would be our portion, would be A, B, D, and E. Our second portion is B, C, and D. And if we were to find absolutely everything, that would be A, B, C, D, E. Okay, and what we're looking at first is our masses. So our mass, and we're looking, the question they asked for it is in the x direction. Do we only see it in the x direction? Oh no, sorry. What we can see from here is actually the shape is symmetrical. So we know that the y is going to be sat on this line somewhere here. So all we need to do is find the direction in x. So that makes it a little bit more simple. So we have our mass here. So what we can say is from our first point, it would be 4a squared, our squared row, and our BCD, well, the area of a triangle is equal to half times the base times by the height. So we know the base and we know the height. So that would be 1.5. Half times the base, we'll make it simple. So it'd be 1 times by 3. So that'd be 3a squared row. A, B, C, D, we'd add these up and we'll get 7a squared row. The next column we're going to be looking at is the x coordinate. So we know our first point here from A is just 2a divided by 2, which is a. And our second one, as we've just found out earlier, that this is going to be a third of the height of the triangle. So therefore, that would be 2a plus a, which is 3a. And so it would sit somewhere about here. And likewise, that would be called x bar. So if we would then multiply these together, which would be mn xn, we would find that would be 4 a squared row times by a, and it would be 3a squared row times by 3a, and if we added those together, we would get that would be 7a squared, so 7a squared row multiplied by x bar, if we multiply these two together. Okay, so all we're doing here is using this table to help us simplify, and if we were then to use our simple equation, we were to start working our way down here. We were to then say that that would be 4a squared multiplied by a plus 3a squared 3a squared multiplied by 3a, 3a squared multiplied by 3a, and that would all equal 7a squared row x bar. If we were then to stick that into our calculator, we would find that x bar is then equal to 13a over 7, and then this will give us our distance of our x bar, which would be our centre of mass. So do be careful and see if you do see some lines of symmetry, you can probably simplify your calculation quite a bit. So that was just centre of masses. Next, we're going to actually look at how we do some acceleration and how we move forward with